All right, so welcome everyone this morning. If you are registered for this class for seminar credits, please make sure you sign in at the back of the room. And today it's my pleasure to welcome Amin Arbabian from Stanford University. He's an assistant professor in the electrical engineering department. And like many of us, he does research mainly on new types of circuits and architectures that are integrated on a chip. I think one of the things that's interesting about Amin's research is really what's driving chip research in today's environment. It's really not the technology that's driving new chips and research into new architectures and circuits. It's really on the system side. And this is a nice example of that in the medical area. So I think a lot of the work that he's going to describe is related to his research on medical devices. So just a little bit about his background. I won't read too much, but he received his PhD in electrical engineering from UC Berkeley in 2011. He became an assistant professor at Stanford in 2012. He's very active in the IEEE. He's on the technical program committee for the RFIC and the European Solid State Circuits Conference. And he has won a number of career awards, two of which I'll mention, the NSF Career Award in 2015, and I think that's for research related to his talk, and the 2014 DARPA Young Faculty Award. He's also won a number of Best Paper Awards, including at the International Solid State Circuits Conference in 2010, VLSI Circuit Symposium, the RFIC Symposium twice, and the MTTS Bio-Wireless Symposium, which I'd actually never heard of until I just read this, and BioCast, and a couple other conferences, but in the interest of time, I'm going to turn it over to Amin.
Thank you, Chris. Good morning, everyone. So my talk is titled Nyquist-Rate Healthcare, but essentially what I'm going to talk about today is that the circuit designer, electronic systems, how does our work sort of relate to the broader problems in healthcare. So I try to sort of get into that problem a little bit and motivate it and hopefully discuss some of the technologies that are related in that space. So before I get started, I'd like to start from giving you sort of an overview of my lab at Stanford. So if you look at my lab in terms of expertise or background, there are three sort of subtopics in my group. First is RF to millimeter wave systems, designing chips for imaging, for communication, packaging, moving above 100 gigahertz, integration between the chip and the package and the antennas. There's a second area sort of in my group that I'll kind of talk about a little bit today, looking at imaging applications, specifically geared towards medical imaging. And the third part are ultra-low power devices, areas where miniaturization and ultra-low power sort of derive the need for integrated circuits, custom integrated circuits. But I think probably a more related or exciting way to look at research is to look at applications. So the three broad applications we're interested in is healthcare, sensing, and this terascale IoT side of the world. Now in healthcare, I'm going to talk about that today, so I won't go into the details of this. But the idea is, how do you provide monitoring, therapy capability in a closed loop fashion? We're going to look at implantable, ingestible, and wearable electronics and how they come in, sort of close the gap in Nyquist sampling and monitoring. In sensing, we're focusing a lot on multi-physics approaches. We're looking at combining millimeter wave, RF, ultrasound, optics to provide remote sensing, provide capability for measurements from a distance or measurements of spectroscopic measurements of samples. Thermoacoustics is another area we're looking at. More recently, I've been excited on looking at some of the optical interferometry techniques, again, leveraging what we know from CMOS image sensors, and see how that sort of opens up new opportunities. In the IoT side, of course, these are huge problems, but our angle of attack in IoT is the question of how do you scale things up. We have now today wireless systems that are in the billions of devices. We have about 7 billion mobile subscribers around the world. IoT is projected to be in the trillions. Now, of course, the designing systems that go from billions or trillions are going to be very different. And one of the problems we started looking into for that scaling up is harvesting and wireless power. You're not going to have 1 trillion devices operating on batteries. That's far we know. So we're looking at combination of RF, millimeter wave, ultrasonic, and optical techniques to do wireless power delivery. We've recently focused a lot more on ultrasonics. Earlier, we had work on RF and millimeter wave for power delivery to small devices. We're now doing sound-based energy harvesting and also wake-up receivers. And at the end, there's also activity on wireless fiber. This is an area, if IoT is successful, you need to have the backbone to deliver data across the network at much higher capacity. Now, if you look at these applications, they're again enabled by the same multi-physics RF system array signal processing expertise. But 15, 20 years ago, these slides would be dominated by communication. And today, I think there are a lot more applications emerging. Communication is still a huge problem, lots of interesting areas to look into, large arrays, high data rate communication. But sensing and healthcare have also sort of risen up in terms of priority because we can now apply some of the techniques we learned from communication circuits into sort of other areas. Before I get started, the most important slide of the talk is basically acknowledging the work of students, collaborators, and funding sources. Today, I'll be talking about work of these seven students in my group. I'll be sort of giving an overview of some of the topics they've been working on. Okay, so let's get into the sort of the motivation and introduction of the slides. So, problem with healthcare, I think you can look at it from two different angles. One is cost, and we've seen this slide over and over again, more updated version of this slide perhaps. So this slide basically says that the healthcare costs are rising at an alarming rate, and an unsustainable rate, projected to be a third of our GDP in the next 10, 15 years. So that's one trend that we see, rising healthcare costs. And this is going to be aggravated by the aging population. So the curve is going to be sort of affected by an aging population. And from a naive sort of high-level point of view, you can assume that whenever there's a cost problem, if you apply technology, the cost should go down. So that's sort of one takeaway point. But the more important aspect of it is quality and outcomes. So here, what I'm plotting is the two leading causes of death is heart disease and cancer. And if you go and plot the mortality rate from these two, heart disease and cancer, and you plot them from 1980s to 2010, so this is the technology era for medical imaging. This is the area where we brought in diagnostic tools, interventional tools. You'll see that the heart disease, in the case of heart disease, we've had very, very successful sort of reduction in mortality rates. So that's very exciting. Technology and diet and various other metrics played a role. But if you go back and look at cancer, you see that it's pretty much flat. The mortality rate from cancer from 1980s to 2010, 2015 is relatively flat. And if you see a downtick in 1990s, it's usually attributed to changes in smoking habits in the US. So that is a problem because we have introduced a large range of technologies, but at the same time, we haven't been able to reduce sort of the mortality rate. And the question is, what was the y-axis? So y-axis is per 100,000. So this is death per, I think, 100,000. Yeah. So what is the problem here? So any disease, here I'm focusing on cancer progression, but any disease you can plot two sort of arbitrary axes of progression of disease and time. And for cancer, for example, it starts from not being detectable at all to incurable state of cancer. So the problem is, today, most of our diagnostic tools, interventional tools, are post-symptom. Something happens, you go to the doctor, and then the whole kitchen sink is thrown at the problem, figuring out what the issues are, diagnostic imaging, interventional techniques, surgical techniques. But before the symptom, we almost do nothing. We go to the doctor every couple of years. If you're really up to date, we do our maybe blood pressure, heart rate, weight, and height, and that's it. So the question is, if you look at this from a sampling point of view, this is our screening interval, which is usually limited by cost, safety, or effectiveness of our screening tools. And it's limited. And for different types of disease, the progression rate is different. So for this particular disease, we're not able to find or screen for that disease, for that cancer, in an effective manner. So we end up basically being too late. By the time we detect, it's already too late. Interventional techniques oftentimes don't work out. So this is essentially a sampling problem. And the sampling problem, the question is, how do you sort of close that gap in sort of sampling? But what about the systems we design? If you look at any sort of electronic system we design today, I could have put a picture of an IC, integrated circuit, that has a lot of monitoring, calibration, correction. I've used an example of a jet engine, an example of a car engine to look at these samples. There's a huge amount of monitoring, real-time monitoring, correction going on in any kind of man-made system. So for example, the jet engine generates about 10 terabytes of data per engine per 30 minutes of flight. And the reason for that is we're constantly monitoring the operation of the system. If you try to draw an analogy to the way we look at our bodies, we're not monitoring it at all prior, again, to symptom, prior to sort of the onset of disease. Even the onset of disease is a little bit of a question mark, because onset of disease for us is when it presents symptoms that are visible or detectable, right? So if you wanted to take one slide away from my talk, I think this would be sort of our thesis. The thesis is that if you, again, plot arbitrarily sort of utility in one axis and frequency of testing in the other, there are two major regimes in which technology is applied to healthcare today. One is what I call NIH territory. So NIH territory, what I mean by that is these are advanced imaging diagnostic tools, MRI, PET, CT, fMRI, combination of fMRI and CT. Inside the surgical room, I think Harvard has now this new program where inside the surgical suite, they have the combination of all real-time imaging technologies, interventional surgery. So this is where NIH is working on, and I think we need a lot more of this. This has been very successful. On the other side, we have a lot of activity from startups and small companies and large companies looking at continuous monitoring. So the frequency of tests is very high, but the data you measure is activity, heart rate, and things that are not directly actionable in terms of making decisions for health. And so the question is, can you sort of bridge that gap and operate in what we call this Nyquist health regime, where you're doing more frequent tests compared to traditional hospital-oriented diagnostic tools? You bring that closer to the patients. And at the same time, you provide more valuable data compared to heart disease and so forth. So how do you get there? I think one part that as circuit designers, electronic systems, RF systems, we come into the picture is we need closer integration of these electronic systems that monitor and apply therapy with the human body. We need to bring these tools from the hospitals closer to the patients. And that's not what NIH and FDA are focusing on. Their methodology, the way they operate, their approval rates, is everything is pushed into the hospital and the clinic. And what we're talking about is how do you bring it closer to the patients? Another aspect is you need a wide variety of electronic-related systems. You need sensing, monitoring, therapy, and closed-loop delivery for this to be successful. And today I'm going to talk about implantable, ingestible, and wearable electronics. Some example projects, small steps in this direction. This is obviously a big problem. There's a lot of work to be done. We're making tiny steps towards sort of these goals. But this slide should give you sort of an overview of how I see the problem of healthcare and how I see electronics being applied to healthcare. So today's talk, I have three main topics. I'm going to talk about implantable system, a little bit on ingestibles, a couple of examples of ingestible systems looking at the GI tract, and then portable and wearable screening platforms, providing that sort of Nyquist monitoring. If time allows, I'll have a sort of a new project we launched is sonomagnetic stimulation, SMS, getting into stimulation actually without being invasive, neural stimulation without invasive. So one of the notes I wanted to say is that I've covered a little bit of why we look at these problems. I'm going to tell you what we're actually going to focus on. But for some of these projects, I'm not going to be able to go a deep dive given the time we're focusing on these things. So if you're interested, please come with questions, send me email. I'm here after the talk. I'm here today. I'd be very excited to talk about any of these projects that I'm going to give you examples of. Okay, so let's get started with implantable systems. So the reason we got excited about implantable is this emerging paradigm of electroceuticals that's been looked at in the past decade, sort of picking up in terms of interest. And here the idea is you're replacing chemical drugs, systemic application of chemical drugs with electronics. And the idea, the core of the idea is by overriding and controlling the organ function. And the way you do that, overriding and controlling the organ function, is you control the nerves that control the organ. So the nerves that go into the organ, you control that. You also have real-time measurements of the outcome of the function of the organ, and you put that in a closed-loop fashion. And the applications of this obviously go way beyond neurological disease. So we're talking about arthritis, asthma, immune system, hypertension, diabetes. So none of these are neurological diseases. These are different organs in the body. So you override, you take control off by this closed loop stimulation and measurement. So any sort of neuromodulation electroceutical has three main components. Number one is you need to measure the physiological, the biological sort of state of that organ or state of the body that you're interested in. So that's the first thing, which is basically you're measuring the health status. This is the recording. Just like any feedback system, you take that measurement, you compare it with the ideal state or the targeted state. So that's our diagnostics. And then the third part is treatment. So you apply stimulation to the nerves. You control what action needs to be taken to change the state of the organ, specific organ. So these three parts, looking at it from an electronic point of view, that closed loop operation requires four components from electronics. One is we need to sense, we need to measure. Number two is we need to force, we need to actuate, stimulate, whether optical, electrical movements, delivering drugs. And then we need computation, some external computation that has models to compute what the right state is and how do you close the loop. And the fourth one is you need duplex communication. You need to be able to communicate with these devices that are in the body and need to take measurements out of the body. So you need that duplex communication. And obviously, if you want to apply to a broad range of disease, you need these devices to be miniaturized. Right? So complex functions, we're not talking about implantables that are doing very simple functions. These are complex implants that require a high level of power, and they need to be reliable and operate at depth. So this is sort of the engineering challenge, sort of boiling down that sort of a big challenge of electroceuticals into what we need to do as engineering side of it. Now, but if you look at the state of implantable devices today, they're far away from what you need to apply to electroceuticals. They're invasive, and primarily, if you look at deep brain stimulation, for example, they're a last resort treatment. You would not go through this treatment if you have any sort of other option because of the level of invasiveness that is applied. So if you're looking at diabetes or hypertension, this is probably not what you're looking at to cure your hypertension. This will probably generate a lot of hypertension, looking at sort of the surgical process. So the question that we started looking into is if you want these complex functions, you need power available at these implants and you need to be deep in. So how do you wirelessly power implantable devices that are miniaturized? They were talking about millimeter scale implantables. The most common way of powering things wirelessly, as your Apple Watch or your toothbrush, is inductive power transfer. And inductive power transfer is reliable, is safe. It's been approved by the FDA for a range of applications. But the problem with inductive power transfer, as you see here, is that as your range to size ratio goes up, as you try to go deeper in and the devices get smaller, it gets less and less efficient to transfer power. In other words, there's a very sharp drop in the coupling coefficient as you try to go deeper or you try to make the implant smaller. So it's not very sort of efficient for kind of applications we're interested in. Well, if inductive power transfer does not work, how about if we try to utilize radiative modes, propagating modes? This is how our antennas operate in the real world. This is how our cell phones operate. We have radiative propagating modes from transmitter to receiver. So sounds like a good idea. Again, there has very nice applications of radiative mode power, but the fundamental problem is if you can look at the wavelength of operation, even if you operate in gigahertz, the wavelength of operation is much larger than your implant. So your wavelength could be 5, 10 centimeters. Your implant is millimeter. That has two implications. Number one, I cannot focus the energy into the receiver. If you've ever designed anything that does beamforming, anything that's beam steering, focusing requires an aperture that's larger than the wavelength. So number one, I can't focus the energy. The result of that is I will heat up large portion of tissue that has safety and reliability concerns. So the FDA will be looking at this and say, well, you're going to have an implant that's going to be running 24/7 for 20 years. I cannot have a heating of the large portion of tissue for these specific applications. Some applications very closer to the skin, this may be perfect solutions. For going deeper in and smaller, this would be a problem. There's a second problem with this is even if you get the energy in, to recover the energy from the implant, again, your device is much smaller than the wavelength. And if you've ever designed antennas, you know that sub-wavelength antennas are not efficient. This is why your cell phones require a considerable size of an antenna to be efficient. If you try to make a cell phone that's much smaller, if you talk to the teams that designed the LTE version of the Apple Watch, you'll have a few of antenna people sort of pulling hair out, trying to figure out how you get efficiency from a LTE band on a sort of an Apple, on a small form factor. Now here we're talking about orders of magnitude smaller than the wavelength. So these are the two problems. And what we started looking into was applying ultrasonic waves. Now the main advantage of ultrasonic waves is that their wavelength is much smaller than the wavelength of RF, because the speed of sound is orders of magnitude slower than RF propagation. So in other words, I can have a megahertz system. I can have a megahertz system that gives me a 1.5 millimeter wavelength. So what that buys me is that once I have a wavelength that's smaller at a reasonable frequency, I can have better focusing. I can focus the energy down to my implant. I can operate with multiple implants. I can beam energy into multiple implants and communicate with the multiple implants. And because the receiver is now a resonant system, it can more efficiently pick up power. So these are examples from other applications, imaging and HIFU, that have focused the energy down the depth. So they focus the energy down into depth of about 7 centimeters, and the focal point or the focal size is still small enough to focus into a single implant or a few implants. So those are the advantages. Side advantages are the FDA intensity limit is higher for ultrasound compared to RF. And the second advantage is the tissue attenuation is lower for ultrasound as opposed to RF. And these two are obviously related. So acoustic power has sort of fundamental advantages, we think, in a specific range of applications where you want to go deep in and you want to have a small implant. So we've been looking at this problem for a while. We started looking at the theory of this problem. How do you focus energy efficiently to small implants? How do you recover that energy? And how do you make communication also possible? Because remember, it's not just about the power delivery. It's that I need to communicate with my implantables, and I need to hear back from the implantables. So we started from the efforts on modeling, a lot of models involving mechanical, acoustic models, and how they interface with electronics. We looked at measurements of sort of power transfer in tissue in vitro. And then we started building our systems. With first generation of systems, we did hybrid communication and some power delivery. We went into stimulation optogenetic. We've done some work on drug delivery where we have electroresponsive polymers that respond to electric fields. So we recover the ultrasonic energy and we pulse electric field on these polymers and they release drugs. We've looked at the beamforming aspects and how do you design the external electronics to beamform, find, and communicate with implants. We've looked at multimodality stimulation, pressure sensing, and sort of a range of applications we've been sort of interested in. Now, today, we're at the stage that we're very close to closed-loop neuromodulation applications. We have 2 in vivo studies running right now, try to take control of specific organs, take control of specific nerves with measurements, and close the loop. So that's one of the areas we're very active. A second more important one is safety concerns. So nobody's been doing these ultrasonic implantables, and so FDA has concerns. So we have projects joint with FDA to look at miniaturized implants and to look at the safety and reliability of these implants over time in vivo. The external device is what we're working on, also miniaturization. So these are sort of our activities in this field. So what are the figures of merit? When you're recovering power, what are you trying to optimize, and why is ultrasonic power recovery more efficient? At the end of the day, the figure of merit that we're most interested in is aperture efficiency, or power conversion efficiency. And what that means is that if I have an acoustic intensity, like imagine an acoustic field, acoustic intensity coming to my implant, and I have a specific aperture of my implant. The question is, how much of that incoming power intensity, milliwatts per centimeter, did I pick up in my limited size implant? So in other words, this is looking at the available electrical power divided by the acoustic intensity multiplied by the physical aperture of the implant. So that's how efficient are you at picking up energy that's directed towards you? This is on the implant side. So we've looked at a variety of different models, variety of different materials. We looked at PZD4, PZD5H, barium titanate. And in all of these systems, if you optimize it, if you could take into account the geometry, the material, the acoustic loading, and sort of optimize the whole chain, you're able to achieve 50, 60% and above in this aperture efficiency. And so this is what makes these implants very different than RF implants, where the aperture efficiency is very low, primarily due to that I don't have the aperture, essentially. So that's sort of one way of looking at the problem. And now I'm going to give you a few examples of systems we built and tested with these principles. So the first version of system we built, this goes back to 2012, is we had a hybrid system. And the hybrid system had essentially a downlink of power and data with ultrasound. And the uplink was taking place in RF. We had very good reason back then that we wanted to have an uplink in RF, especially if the depth is shallow enough. In RF, you have an advantage of higher data rates, and you can duty cycle aggressively because of the bandwidth that are available. So in other words, we have a system that does power and data in downlink, on ultrasound, and data uplink on RF, and we also delivered 100 microwatts of output power as sort of a platform enabling other functions. So in the transmitter chain, so the receiver is coming at 1 megahertz. This is the ultrasonic. It has envelope detection to pick up data. And on the transmitter chain, in order to emulate sort of a communication system, we have a pulse position modulation, sending small pulses at 4 gigahertz to the external receiver. So we're doing data receive and data transmit on a PPM 4 gigahertz system. So pulse-based, highly duty cycled. This is the chip. It's a 65 nanometer. There's not a whole lot to see on the chip, but you can see the transmitter chain, and the rest of it is power recovery, data recovery systems. And this is the full implant system. This is our sort of what I call a generation 1 implantable package. You can see this is our stiff, hard packages, primarily on sort of FR4 type of PCBs. What we were able to do is we were able to communicate from the device out in sort of a 3 centimeters of tissue phantom, and we had enough SNR to do a PPM modulation. But the problems with this first generation were, first of all, I cannot shrink this system further because the antenna is pretty much at its limit. The antenna can't be further reduced in size. It's going to get even less efficient. And second thing is that it's relatively, if you look at the whole system, it's relatively large for the RF side and also for the whole sort of system integration side of things. So that's our first prototype, about 3 centimeters depth, and getting about SNR of 13 dB for PPM modulation, binary PPM modulation kind of thing. So the second question we asked is, well, we can communicate, but can we deliver high power for stimulation purposes? This is a difficult problem because in this sort of applications, you need to deliver 1 to 10 milliwatts of power in depth. And the application we picked was optogenetics. Here you use viral vectors to genetically sort of engineer nerves to be responsive to light. So you have nerves that express light-sensitive ion channels. And as you stimulate with light, they'll fire. So this is how you do neuromodulation. So we picked this application because neuromodulation in terms of technologies for small animals, I think this technology we have today is sufficient. It's actually working great. But what if you want to go to large animals and you go deeper in? That gets more and more challenging, so we started looking at this application for sort of demonstrating stimulation purposes. So the power levels that we're looking at is 1 to 10 milliwatts. These power levels are unprecedented if you look at wireless power transfer across especially 4 or 5 centimeters. With ultrasound, the idea was, can we deliver this much power? So this is our setup. I don't know if I can play this video. Here we go. So what I'm showing here is that we have the implant. Again, this is our sort of generation 1.5 packages. Again, hard material, LED on one side, and then the chip and the system on one side. And then going through tissue, and you can see the LED sort of firing up. You should be able to see the LED sort of firing up down here. Now, if you look at the acoustic intensity and optical intensity, for our purposes, we're looking at about 6 to 8 milliwatts per millimeter squared of optical intensity. And we can achieve that at acoustic intensities that are much lower than the FDA-allowed continuous intensity. And we can do that for about 20% of a duty cycle in optogenetics. So 20% is sort of the maximum kind of duty cycle that you're probably operating in optogenetic applications. So stimulation could be done at relatively high power levels. The third question was, can you do full ultrasonic links? Because we want to further miniaturize these systems. And so we started looking at an FDD system which does power and data, everything on ultrasound. So there's no RF here. We threw the RF out the door and we said everything in ultrasound. And so the downlink is operating at about 1 megahertz. So downlink power and data comes at 1 megahertz. So the FDD system operates at about 2.5 megahertz transmit, so avoid harmonics at the receive. So we're achieving about 25 kilobit per second on downlink and about 100 kilobit per second on uplink and on-off keying. So here we use the 10-bit PRBS on the chip to be able to do bit error rate measurements, and our peak power on transmit is about 125 microwatts. So these are our second generation of packages. Again, you can look at polyimide substrates, soft material, looking at epoxies, moving towards sort of biocompatibility. Today's talk, unfortunately, I'm not going to talk about packaging. And I think packaging and biocompatible packaging is highly underrepresented in terms of publications and science sort of journals and papers. It's not as attractive in terms of research, but it's a very fundamental problem, as we have learned the hard way, I should say. So we're looking at second generation packaging. This is our chip. This is our cross-section of how we built the air cavity under the package. Presented this at ICC last year. And again, going through tissue phantoms, and we're able to detect the data. So we're doing full ultrasonic links, about 6 centimeters of tissue, considerably smaller, considerably deeper than if you would have done with an RF system. Now, number 4 was we built in the communication and stimulation, but can we increase the complexity? And for complexity, we're thinking about something that has bimodal stimulation, both optical stimulation of nerves for optogenetics, and simultaneously electrical stimulation for electrical stimulation of capture of nerves. And the difference here is all the electronics to control the waveform generation, the programming of these waveforms are sitting on the chip. So what the external unit does, it sends the commands, I want these many waveforms, these many pulses at these frequencies, and repeat it for this long. And the chip itself will take over and start stimulating. So a little bit more complexity shifted to the implant for reliability concerns. So this is conceptually what we're looking at. We're looking at electrical stimulation and optical stimulation shown on the bottom left. The chip is shown in the middle, and this is, again, a second generation package shown on the right. Again, soft substrates, looking at the LED and the electrical stimulation built into one. So this video is supposed to show, if I can play this, this is showing the response. So we're looking at different pulse sequences, a sciatic nerve of a frog, and looking at if the power levels are sufficient to stimulate the nerve. So we're looking at 1 hertz, 2 hertz, and we go all the way to about 5 hertz of stimulation in this particular application. So the power levels are sufficient into this sort of ex vivo, let's call it, application sort of demonstration to stimulate the nerve. And obviously, if you try to look at these data, you need to also benchmark with EMG measurements. So simultaneously, we're stimulating, we're measuring EMG signals to make sure they're correlated to the stimulation. We're now doing force measurements to see if we can elicit a range of specific force based on the stimulation patterns we use. Also, if you look at the strength duration curves, you see that the threshold drops as expected with pulse width, and the charge deposited in phase sort of has an optimal point as expected. These are sort of confirmed with theory. The 5th function we wanted to demonstrate is essentially precision sensing. So I've showed that I can do stimulation, we can do communication, but the last missing piece of the puzzle is, can you do precision sensing of physiological or biological parameters in depth? So we picked here pressure, because pressure has a large, sort of broad range of applications. Our specific application that we've been working on is bladder control. We want to take over the bladder function by measuring the pressure in the bladder wall and then controlling the sphincter through the pudendal nerve. So if someone's bladder is non-functional, we just override it with a feedback system. But pressure has applications in blood pressure, local blood pressure in specific arteries, or local blood pressure in different veins in different parts of the body. So we picked it as sort of a broad enough application space. And the idea is, again, you would integrate everything on the chip. You have bidirectional communication. Here we're doing a TDD sort of communication. I'll talk about that a little bit. And then you have your pressure sensing device sitting on the same package. So the electronics here is about a 10-bit, think about a 10-bit SAR ADC, giving you about a sub-millimeter mercury of resolution in terms of pressure. And if you look at the waveforms, these are our measured waveforms we presented at VLSI last year. There are different sequences on how you power up and communicate. The mindset here was you want to avoid ultrasonic waves when you're measuring pressure. Because one of the things, again, we learned the hard way, is that as you have ultrasonic waves in tissue and you try to measure small variations in pressure, they will interfere. So the way we operate this is a full TDD system. You start with a packet of energy and data. which is the ultrasound downlink. So power and data goes to the ultrasound device, to the implant. Then you have a quiet zone, the wait time, to make sure all ultrasonic waves have died down when you're measuring the pressure. Then you start the pressure measurement, and then you transmit that out. So this is the ultrasound link sending the data out. And then the next sequence starts. And if you look at how we're operating this, we can go up to about 1 kilohertz of sampling. This is far more than enough for most applications in biology. Nothing changes at faster than 1 kilohertz, more or less, in terms of pressure at least. So we're measuring up to 1 kilohertz of sampling. Our range is about 400 millimeter mercury to about 1200. A full bladder at sea level or beyond sea level, below sea level, up to the empty bladder at 30,000 feet sort of thing. We wanted to cover the whole range. And our resolution is about 0.78 millimeter mercury here. So these are, again, our packages, soft packaging material. You can see that we've moved into a long packaging system because our surgical partners have been insisting longer packages to be able to inject these implants as opposed to open surgery. So we're moving towards minimally invasive surgical techniques on the sort of the same platforms. One of the last things we did on the systems is we actually used the same transducer for both transmit and receive. If you've designed duplex systems, you know that there's a lot of concerns here on how the transmitter and receiver will interfere with each other. So you have to build the electronics on the chip to make sure that interference is mitigated and we have reliable operation. But doing this will shrink the size of the package because now you have only one transducer doing the whole thing on a TDD system. Now, the next question is, we've shown you all the basic functions, but what about communication externally? So the external device that communicates and finds these implants, how about that part of the system? Phased arrays in ultrasound have been around for decades. For medical imaging, people have been using 1D and 2D phased arrays for a very long time. The concern here was that the application we're interested in has different constraints. We're interested in power delivery. We're interested in communication with different implants simultaneously. And we want the system to be flexible enough to go from one mode to the other. So for example, if you're communicating with implants, so you're sending power and data, and then you want to hear back from multiple implants, you should be able to go from one mode to the other sort of on demand in a flexible fashion. So we needed to sort of have custom electronics on the external side. So we went about and designed the whole thing, including the transducer array. We have a 32-element array on PCT4, about a megahertz operation. We have a full programmable external electronics. It's a combination of an ARM processor and an FPGA control that you can pinpoint to different parts of tissue. You can deliver power packets or you can deliver data packets. So here on the right, I'm showing measurements using a hydrophone, pressure measurements in a hydrophone. And you can see that beam steering function, obviously. And we can do simultaneous multiple beams. So this is essential because I want to talk to multiple implants simultaneously. And so I need to generate multi-beam sort of functions. And as you can expect, when you have a multi-beam, you sacrifice the number of elements in each of these beams. And so the beam width, the beam widths are slightly larger. So here are measurements. I have two implants 3 centimeters apart in a PDMS and gel sort of a packaging. And if you could see this, you can see that the implant on the left firing and then the implant on the right. So if the projector actually shows this, that you can do time interleaved firing selectively of different implants. So those are the sort of the functions we're showing here. Another part is FDA collaborations. We've been working with the FDA to build more durable packages for in vivo. The packages on the left, we actually had implanted in their system. We ship it down to them. They implant it in vivo. And so far, this one has worked for a month without any observable issues. We have a next generation of packaging that we're sending to them to look at sort of longer observation times. So this is also a very important area. I don't, unfortunately, have a lot of slides on looking at packaging, but I think it's a central piece of the puzzle if you want to make it a widespread sort of application. We packaged this. We built the whole thing, and we sent it to them to do the testing independently at the FDA site. They want to have independent control on how they do the measurements, their setups, so we don't do anything with that. We just ship a bunch of these packages, 5, 10, 20, and then they'll take all the measurements. So we built everything of these, everything from scratch, from the chip to the package, to the coating, to Parylene C, to epoxy, to PDMS, everything is built in-house. A big question here for us has been, if you operate with ultrasound, there are fundamental problems. And one fundamental problem is data rate. I talked about 100 kilobit per second. What if your application requires megabit, 10 megabit per second? Now, most biological parameters or applications do not require 10 megabit per second coming out of the body, but there are a few that do require it. So what do you do then? So we started looking at a line-of-sight MIMO system in ultrasound. This is an area that I've been working on in millimeter waves. And we said, well, can you apply this in ultrasound? And lo and behold, yes, you can apply it. There are waves or waves. And waves become orthogonal at the right wavelength. And orthogonal waves, you can have multiple modes. So we demonstrated that you can double and quadruple the capacity of these links using ultrasound MIMO. And I think that shows you a roadmap. We haven't shown the entire feasibility of 10 megabits per second. But at least we're showing a roadmap in which how you would obtain 10 megabits per second. So we're going to we presented some of this at Applied Physics Letters last year, but we're going to do a little bit more data and more specific analysis in CICC this year. What about molecular sensing? I showed you pressure sensing, but it's not specific. It doesn't have molecular sensitivity. So we're working with Professor Tom So to build aptamer-based detectors on top of these implants. Now, for the first time, if we're successful, this is a very challenging project, primarily because of packaging and heterogeneous integration. Very challenging, but if we're successful, I think we show a roadmap towards in vivo and molecular specificity in real time to give you longitudinal data on how these protein levels are changing and perhaps identifying the onset of major changes. So that's one area. Changing gears a little bit, another aspect is the GI tract. So if you have implantable systems that go into tissue and they're static, another platform that's been very interesting, I've been very excited about this, is wireless capsules, where you have a capsule, it goes through the GI tract, and it can monitor and probably even deliver drugs as it's passing through. It's a disposable platform. You throw it away. It's a one-time operation. So we have two projects in this space, and primary reason we're going after these projects is that there are a lot of disease in the GI tract, cancer, IBD, IBS. But more importantly, there's been a lot of interest looking at the microbiome population in the GI, in the gut, and relating that to the immune system, relating that to the health status. So we have two projects in that space. One is a ultrasound imaging pill cam, collaborating with our friends in the medical school and Professor Pierre Kuriakub in the EE department. This pill will provide radial ultrasound images at 4 frames per second for 8 hours, and it continuously transmits that data out. So you get ultrasound images for about 5 centimeters depth going through the GI tract, through the entire GI tract. And the second project, we're doing a microbiome sort of measurements, proxy with oxidation reduction potential, ORPs, to be able to follow the redox potentials and follow the microbiome sort of changes in the gut. So these are sort of preliminary studies. The one on the left, we made a lot of progress. All the chips have been built and tested and working. What we're doing right now is building the whole systems, which again is a major part of most of these sort of activities. And one new direction, I'm not going to talk about this a lot, but a new direction we kicked off about 1.5 years ago was an implantable microscope. So optical imaging has been very powerful. Optical imaging provides high resolution, functional imaging in vivo, real time. The major problem with it is scattering. If I want to go deep in, photon scatter, I'm not able to image at depth. So what we're building here is a microscope that does its local imaging, multimodality, multiphysics, photoacoustics, and optical, but then transmits the data out. So you place your microscope into tissue, it's doing local imaging, but it's wirelessly sending the data out. From a complexity point of view, it's probably one of the most complex projects that I've ever been involved with, because not only you're harvesting and data communication and everything we talked about, but we have a full-fledged 16-element CMOD array, full ultrasound array sitting on the same system. So imagine running a phased array system, 16 elements, 30 megasample per second, A to D, beamforming, averaging on the same chip that's harvesting energy from external sources. So, but it will, if successful, it will open up applications in this broad sort of space of optical and multimodality imaging at depth. Okay, so let me sort of change gears here a little bit and go to the last part of my presentation, a few slides on imaging. So we talked about implantables. I want to now shift gears and come outside the body and talk about wearables. The introduction here should be clear. Again, we're looking at Nyquist health. So the modalities we're interested in are the ones that can scale down in size and cost to a form factor that we can be on the patient, not in the hospital. So primarily, we're looking at ultrasound and microwave. The other modalities are very powerful, but they're going to be limited to the hospitals in the foreseeable future. You're not going to be a portable, wearable device doing MRI anytime soon, unless we change anything with the physics. Okay, so what about microwave imaging? This is a topic for a different talk. I'm not going to get into microwave imaging, but the idea of microwave imaging is that the contrast is advantageous. Dielectric contrast exists and gives you water content, blood content of tissue. The problem with it, though, is that there's a fundamental trade-off between penetration depth and resolution. If you want to go deeper, you use longer wavelength. Longer wavelength doesn't give you resolution. And so it's great modality if you're close to the skin or if you're operating in regions where the fat tissue dominates and losses are lower. So that's where microwave imaging will sort of emerge as a supplementary or complementary sort of application area. But what about broader sort of applications? So when I started at Stanford, we started looking into physics of electromagnetics and looking at if there are alternative ways to leverage this contrast. And lo and behold, there is a modality out there, thermoacoustics, which operates by the fundamental function of exciting tissue with microwaves or optical. And then the differences in absorption, because of your dielectric contrast, will generate small changes in temperature, millikelvins of temperature. And that gives off a sort of a expansion at the same frequency that you're exciting, and that's the ultrasonic response that you measure to pinpoint the location of these targets. So differential heating will generate differential expansion, and that the differential expansion generates ultrasonic waves you pick up. So this is thermoacoustics. This is the physics behind photoacoustic imaging. There are other modalities in which ultrasound and electromagnetics interact. One of them is Lorentz force magnetoacoustic, where you have a static magnetic field. You have Lorentz forces that generate the ultrasound waves. And there's also electroacoustics, when charges respond to the ultrasonic fields. So thermoacoustics actually goes back to Alexander Graham Bell. This is his paper talking about thermoacoustics. He used light sources, sort of intermittent pulse light sources, and he could generate sound waves with these light sources. In fact, had a patent called photophone, and I think he thought that that's more valuable than the telephone because you can do wireless sort of delivery of sound with optics. So the technology goes back a long time, but the reason we got excited about it is twofold. One is we can decouple resolution and depth. The fundamental problem in microwave imaging is with resolution and depth are coupled together, and you can't, they're joint at the hip. We can decouple them. The second is both of these modalities can be integrated and scaled down. So you can conceptually see a system where you have interleaved arrays of ultrasound and RF systems exciting and detecting to provide imaging capability. So what is the problem? It sounds like all good and great, but the problem is the transduction is weak. The transduction between RF and ultrasound is very weak. And traditionally, to overcome this weak transduction, we've used very high power sources, magnetron, klystrons, megawatts of peak power to overcome this weak transduction. One of the things to keep in mind is that in thermoacoustic imaging is a nonlinear phenomena, in the sense that the pressure you receive is proportional to the power you put in. In other words, the power you get out is proportional to the power you put in squared. So that has consequences in terms of pulse width and peak power. But when we came to this problem, we decided to apply two of the techniques we know very much in the details of from communication systems. One of them is coherent processing. The other one is beamforming, and see if that could be applied in this particular field. So let's look at the first one, coherent processing. We know in radar, we avoid pulse radar for many of the same reasons, peak power requirements. We go to CW radar by providing a coherent means to process, to transmit, and receive. So that's SFCW radar. That's your chirp radar. That's the radar sitting on your car. They're all some sort of coherent processing. The problem here is our idea was to apply this coherent processing idea to thermoacoustic imaging. The problem, though, is in radar, everything is a gigahertz microwave signal. Go out 60 gigahertz, you come back at 60 gigahertz. Here, I'm applying a gigahertz signal in RF, and I'm detecting an ultrasound in the megahertz regime. So how do you make that coherent? And this, what we decided to do is we take the RF signal, we first apply envelope modulation, like an AM modulation on top of it, which is at the megahertz frequency. Then we apply our modulation scheme, whether it's chirp or SFCW, on top of that envelope. So now we've provided an avenue to do coherent processing between the transmit and receive. One problem with it is who does the demodulation? I know how to modulate, but how do you demodulate that carrier? Again, going back to the thermoacoustic is a nonlinear phenomenon. It's a square function built in. So the demodulation, the AM demodulation effect, happens for free. just because of the physics of thermoacoustics. So now I can do coherent processing between transmit and receive. I can apply this to what we call a step frequency continuous wave system, where you step your frequencies on the carrier from 1 megahertz to 2 megahertz, for example. And at every frequency, you measure amplitude and phase. Or you can do a chirp-based system. And the only thing you have to take into account when you do a chirp is that because the signal that comes out is double the frequency of the receive, your match filter has to be tuned to the double frequency in ultrasound compared to the transmitter. So coherent processing allows us to get better SNR, so we built a chip. The chip essentially has all the features built in. We can do pulse-based FMCW and SFCW imaging modality, and it has an oscillator, a mixer, a modulator, and a PA. The PA in silicon provides about 25 dBm of output power. Then it goes to a gallium nitride PA to give you the larger peak power required for our application. And the whole thing is from 1 gigahertz to 3 gigahertz. So we're providing a broadband system potentially to do spectroscopy measurements in RF side. So the absorption of RF also changes across frequency, as you see these measurements here. So these two targets will show up differently at different RF frequencies. So we're trying to do spectroscopy and imaging in one shot, if that makes any sense. So if you look at our entire system, because of this integration coherent processing, we've been able to integrate it in sort of a form factor that is more manageable. We obviously haven't yet integrated on single chips or small systems. Well, we have an FPGA that does all the data capture, all the processing, waveform generation. We have our chip that generates the modulation, the output power, the whole chain, signal chain. And then we have a high-state, solid-state power amplifier that's doing the output power to the tissue. So these three components are all in solid state. And for the first time, we're doing thermoacoustic in full solid state without any vacuum sources. This is a comparison between pulsed imaging and FMCW. And as you can see, our SNR is improved drastically. In our particular examples, between 20 and 30 dB improvement in SNR. And here's the imaging of more complex tissue structures with the same methodology. So that was technique number one. Technique number two is RF beamforming. So RF beamforming, we know in RF systems, we've been applying RF beamforming to a variety of applications. Here we've applied it because if you have one beamformer, you primarily heat the surface. And if you have multiple beamforming, you can put the hotspot into depth, and it can also beam steer that around. So potentially, I can generate a hotspot that moves around the tissue for my thermoacoustic imaging, bringing the peak power up. Remember, the resolution only comes from ultrasound. So these are not affecting resolution at all. What we're interested in is just putting more energy and for differential heating for thermoacoustics. And this is sort of our prototype we built to replicate this conceptual design, multiple antennas sitting on the side to generate the beamforming profile. And the measurements of this with one applicator going to two applicators, you can see the SNR improves again. All of these are coherent processing, obviously. And then our latest measurements, we actually went into taking a tissue sample and ablating the tissue sample and seeing if you can target and identify the location of these ablations. So these are standard measurements done for new modalities to show that we have contrast. We have resolution. We've seen the resolution is sufficient. But the question is, do we have the contrast? And these ablation measurements show that we're stepping towards those applications in which we do have contrast. And another project in the same space is, can you extend it further to make it more miniaturized, to potentially put on a phone to measure your blood vessels for biometric applications? So here, we're 3D reconstructing the blood vessels in the finger, and it turns out the blood veins in all of our fingers are different. Could be used for biometrics, could be used for health reasons also. And so this is the system we're proposing. And so far, we don't have the whole array. We have a sort of a scanned version of this, but we've been able to do semi-biological measurements. This is on a scallion plants that you can see the vessels. These are the vessels in the scallion plant. And this is an earthworm, the cross-section of the earthworm, that we can see the blood vessels, or the cross-section of that blood vessels in an earthworm. So we're moving a little bit more to in vivo, I would say. These are semi-in vivo. Obviously, this earthworm was not alive when we were done with the measurements, needless to say, but we're moving towards sort of those in vivo measurements. Last point is non-contact imaging. And I have a couple of slides here. I'm not going to get into the details, but a few years ago, DARPA was interested in applications where you do the same sort of modality, but you do it without contacting the sample. Now, my interest in non-contact imaging has always been removing the operator dependency. If you want to have a wearable device, if you want to have a device that people can take home and do imaging, you can't have it be operator dependent. You can't send a technician, ultrasound technician, with the device at home. So you need to have complete removal of this dependency to the operator. And one way to get there is non-contact imaging. But non-contact imaging in ultrasound is a big problem because the impedance mismatch between tissue and air in ultrasound is huge. You lose 65 dB of your signal when you go from tissue to air in ultrasound. You go from 1.5 megarail to about 400 rail in terms of impedance mismatch. And that's the fundamental problem. Turns out the mechanical noise floor is lower. So you lose about 30 dB in SNR. So in order to combat this problem, we have two sort of avenues. One, we use much better detectors. We use MEMS-based CMOD, capacitive micromachine ultrasonic transducers. We use CMOD detectors that are much more sensitive, getting close to the mechanical noise floor. And at the same time, we applied our sort of signal processing with coherent processing and arrays to the same problem. So I'll show you what we sort of demonstrated to DARPA towards the end of the program. And here is a sample. You can see the target in embedding. This is highly dispersive agar embedding, very lossy. And we're trying to image the location of this thing and then reconstruct this from a distance. So we're doing now non-contact reconstruction. And as you see, as I generate a larger and larger aperture by SAR, I can focus down to the target and focus my energy there. And this is for one target imaging, two targets imaging. So we're slowly getting more and more advanced in that area. So I think I'm out of time. I will quickly talk about the last application space. This is a new project we launched. It's called sonomagnetic stimulation. And the idea is, can I stimulate nerves completely non-invasively? So all neuromodulation systems need sort of stimulation. In order to stimulate non-invasively, you need to generate local electrical currents at depth. So I need to generate electrical currents at depth that are very localized. But we know we cannot do that because RF wavelengths are large. DC voltages, DC currents can't be localized at that specificity. So our idea is, can I use ultrasonic waves to go in and vibrate the ions in a static magnetic field? So I have a static magnetic field, and I move the ions up and down. Now, the Lorentz forces will generate orthogonal forces on these ions. As they move up and down, there's a static magnetic field into the plane, and the charges will move in opposite directions. That generates currents. So we call Lorentz currents. So the idea would be that you have ultrasonic stimulation sitting outside, focusing to different parts of the brain. You also have a big magnet. This could be your fMRI magnet. And then by combining these Lorentz forces, you can localize the ultrasonic field and locally generate electrical currents. That's how we sort of crack the code on localized stimulation tissue being non-invasive. So we did some early measurements of this. Of course, this is going to be, if successful, this is going to be a large project. We can't sort of attack all the problems at once. So we started with an in vitro setup. So we said, OK, I have an ion solution. Can I generate currents locally at a distance with ultrasonic waves? Can ultrasound energy transfer to electrical energy through these Lorentz forces? And so this is what we published in APL last year. And we're sort of showing versus our models. And we've been able to successfully capture those nuances. So in conclusion, I talked about this idea of Nyquist-Rate healthcare. How do you bring sort of electronics, learn what we've learned from consumer electronics, from communication systems, apply to healthcare. And with consumer-centric solutions that bring these solutions closer to the patients, I talked about implantables, ingestible systems, wearable systems. I think this is a very exciting time for electronic design for those of you interested in circuits and understanding the basics of detection, imaging, signal to noise, precision measurements. This is exactly what type of skills needed for this particular area. Of course, there are lots of different areas that I didn't talk about related to our topic. One important one is other modalities that enable Nyquist-Rate healthcare. Any kind of in vitro blood test, people are talking about sweat analysis and so forth, urine analysis. We haven't talked about those. False positives are a huge problem. I have actually a whole 20-minute talk on why false positives are central when we're trying to do Nyquist-Rate healthcare. If false positives are high and you do more frequent testing, you're going to be in trouble if you have the same methodology applied to the screening system. But if you apply it in the right way, if you look at differentials, if you look at tracking patterns over time, you can actually knock down the effective false positive when you're doing more frequent tests. But it's a very subtle argument there. False positives have to be maintained. Role of analytics, we haven't talked about that, but analytics will play a major role in any of these analyses when you're doing frequent tests. The quality of your measurements need not be exactly the quality of measurements you do in a hospital, because I'm trying to measure something else. I'm trying to track and screen. I'm not trying to diagnose necessarily. And then last but not least, biological interfaces. I said chronic implants are a huge problem. How do you make an implant operational for years and years in the body? How do you design the packaging for that? How do you make it reliable, electronics? Not easy problems, because you don't want to go back to the hospital over and over again to change your implants. If you're going to have 10, 20 of these things in the body, it needs to be safe, it needs to be reliable, it needs to last forever. So it generates a whole new paradigm in terms of packaging concerns. So with that, I'd like to conclude, acknowledge again the work of the students. All of the work I talked about, the ideas, the inception, the design, were the work of some of the greatest students I've ever worked with in my group. And also the collaborators. We've been lucky to work with a very creative, I should say, and very knowledgeable collaborators at Stanford and beyond, and also the funding agencies. Thank you.
All right. It was an excellent talk. Any questions? Please.
There seems to be a contrast between your approach of having very few neuromodulation channels on a single chip or single system to the other approach of putting many, many channels on the same interface. Do you see that being the trend of having maybe one or two stimulation recording channels on a single implant, then having many of these implants in the body?
I think that's very good. So the question, if I wanted to quickly repeat it, is what are the trade-offs in having lots of channels on one larger, probably larger implant, as opposed to fewer channels on smaller implants? I think that question is application specific. If we get closer to the brain, I'd like to have a coordinated measurements on a large set of neurons, simultaneously time-stamped, coordinated. That often requires more channels than recording. When I get closer to peripheral nerves, then I have fewer channels to measure and stimulate. Oftentimes, the more channels I have is for reliability purposes or multimodality. But there are interesting questions that come out of your question. And that is, what if in the brain, I'm not trying to reconstruct from a specific part of the brain, I'm doing some kind of a study, some investigation, some discovery, and I want to access the larger sort of cross-section of the brain, a lot more implants. Each of them could be now 16, 32 channels, doesn't have to be 1,000, but I have a lot of them. We believe in the specific areas that will open up new avenues. If you can do coordinated, time-stamped network of implants that can tell you what happens here versus what is stimulated there, you can look at the circuitry in the brain. So it opens up some avenues. But traditionally, you're right, has been larger recording from single sites, or in peripheral nerves, just one or two recording and stimulation on the PNS side. Very good question, yes.
More questions?
Yeah, I was just curious about charge storage. So when you do stimulation, for example, you have a certain intensity and for the given efficiency of conversion, you may want to be able to, for example, stimulate at a much higher rate. I noticed your dashboard had a good bit of decap.
Yes.
And I was curious, as you sort of look at the applications you're looking at, do you feel you'll be able to get a lot of that stuff on decap? Are you going to rely on external? What portion of your existing package, what's your decap reliance today?
Actually, that's a very good question. So the question is, we have, in a lot of our systems, we have relatively large decap. Except for the first one, which was completely on chip, all the newest ones have reasonable size, or I would say large size decaps off chip. So the schools of thought are different here. One school of thought is I'm going to real time provide the power and data to do stimulation. So I'm doing it, so if you go back to our pressure sensing operates in the following way. I provide a commands to measure pressure. The implant measures pressure and sends it back, and it's finished. There's no memory involved, everything shuts down. The next pulse comes in, I measure the pressure, and I can do that up to about a millisecond or 1 kilohertz frequency. So that's one school of thought. You say, everything is external, I just need the energy that sits on one measurement cycle. And there, I think our capacitor needs are slightly smaller. If we've made it larger, it's probably for a lot of times for reliability concerns and making sure that we can get it operational. But we've also played with our first implant. If you look at our first generation, that had a couple of nanofarads capacitor on the chip. was trying to do a lot with that external chip. But as soon as you bring it outside, you want to do a 100 microwatt system, you need some external capacitance. Now, second school of thought is I send the command in, and the capacitor has to be large enough to stimulate for 5, 10, 20 pulses. And that puts a lot of burden on the capacitor. So those are the two spectrum. And we've been operating somewhere in the middle. So we, for example, our stimulator chip has a set of commands that go in and provide the stimulation parameters, but I need not send the stimulation parameters waveforms every time. I can just send packets of power, quote unquote, for repetition. Having larger capacitors than what we've worked on will probably at some point generate issues with the energy density, safety concerns, and so forth. So we've been going up to a limit where we know it's safe enough in terms of energy density and the sizes. I think after that, if you look at supercapacitors, things more dense, it'll be a reliability concern, leakage, and long-term operation. But from a research point of view, I think that's a very important problem. We haven't attacked it head on yet. We haven't said, what is the power management for a platform implant that does many things at different time scales? We haven't yet done that. But if you look at a couple of our papers, we touched upon this issue. So for example, our BICAS paper, which looks at bimodal stimulation, we have about a page that goes at exactly that problem. How often do you want to stimulate, and how big is your capacitor? And we look at the trade-offs a little bit. But again, peripheral, not from a head-on sort of approach.
More questions? I actually have a couple.
Yes.
So this is really related to power transfer. So you've got ultrasound versus wireless power transfer. And so a couple questions that I thought of. You think of loss in terms of wireless power transfer going through the tissue, propagation loss, right, from the source to the actual device that's picking up the wireless signal. Is there a similar thing that you can think of in terms of like path loss for ultrasound signals, and what's the comparison, and what happens to that loss? Is it dissipated in the form of heat, and is that a problem? And then so maybe I'm asking a huge question, but
that's okay. Huge questions are good.
Then also it comes to mind the source, right?
Mm-hmm.
Practical scenarios for, if somebody has one of these devices and you're doing ultrasound for energy harvesting and power transfer, what is the source and what's the scenario? I mean, wireless power, there's some interesting scenarios. You put a giant coil in your bed and a seat, charge up, while you're there, and then the patient or whoever moves around. And a lot of the energy is stored in the supercapacitor. So I could see a similar scenario for storage, but how about the source? What are people actually thinking?
That's a good question. So the two questions, you had the microphone, so I don't need to repeat the question, I guess, right?
Yep.
So the first question of, how do you model losses? Modeling losses in ultrasound in some ways are easier because I have a smaller wavelength, because I get to propagating fields. Modeling loss is easier than when I do RF. See, in RF, I can come up with a number dB per centimeter if I assume plane waves. But I don't have plane waves in RF because everything's so small compared to the wavelength. Here, I can generate plane waves if I have a single transmitter, single receiver, and I can look at sort of propagation losses. In tissue, propagation losses are about order of magnitude 1 dB per centimeter per megahertz. So if you operate at 1 megahertz, ultrasound has about a dB per centimeter loss, and that turns into heat. But if you look at the heating that this generates and compare that with RF, it's much lower. This is why FDA allows you to put more intensity in ultrasound, because they care about heating at the end of the day. And they allow you to put more ultrasound because ultrasound imaging has been looked at for decades. There's fetal imaging in ultrasound, and they look at safety concerns. And our power densities are, in fact, lower than what you use for fetal imaging in a whole transmitter array, 720 milliwatt per centimeter. So that's one side. How do you model it? You can model it with, actually, we have a paper that's finished right now that looks at the entire link. So the components of the link are, obviously need the power come out of DC supply, turn into RF. So that's what we do, PA and some class E. And then there's a transducer. So the transducer turns that electrical energy to ultrasound. There's the propagation losses that you mentioned, dB per centimeter. But more importantly, there's focusing. Because in ultrasound, I can do lensing and focusing to a near field. So that is the most important factor of all of these things. If I can do effective focusing, I can recover a lot of the energy that would have otherwise been lost. So that model is relatively complex, but we have one shot at it in a paper that we're about to submit soon. And we're, I think, moving in a direction where we have models. We can provide models to say, for a particular scenario, for this size, for this array, here's your link looks like. Now, the second question is, I think, a very interesting question of what are the use cases? The short answer is I don't know. I don't completely know, because it depends on the application. So you can think about everything from a variable, like a Band-Aid model that transmits the data and power to these implants, continuously running, all the way to just like what I do when I'm sleeping at night and I have these big coils to power something. I can power them with something that I wear, or a wristband, or something that I wear overnight. So it depends. If you're doing cardiac pacemaking, which is a very difficult application, you don't want to be out of power ever. Because if you lose power for a whole few seconds and you don't do pacing on the card, that leads to problems. But if I'm doing measurements every hour, let's say there's parameters, biological parameters, proteins, troponin that we're measuring with these aptamers, if I'm measuring every hour or every 30 minutes, that's okay. I can be off in the timing. I can be off by measurements. It's less sensitive. So I guess the answer is it depends on the application. And so far, we've been trying to be as broad as possible. Right starting this year, we've targeted a few very specific applications that I guess in a year or two will tell you how successful these use cases are in terms of patient, in terms of doctors, deployment models, and so forth.
Okay, good. So I think we're running over time here, so let's thank our speaker one more time.
Thank you.